So here's our equation. Delta G equals RT ln concentration in the destination divided by concentration in the source plus Z sub A F delta psi. Okay, so one number that I want to write out here is my Faraday's constant, which is 96,000 or 96.485 kilojoules per mole volt, or per volt mole, doesn't really matter there, because both of those units are going to be in my denominator. Okay, what I'm talking about with this problem is I'm transporting sodium ions in or out of a cell when my delta psi is equal to negative 60 millivolts. Well, one thing that I do need to reconcile is my units here. This is in millivolts, and this is in volts. So I'm going to go ahead and convert this to millivolts, from millivolts to volts, which would give me negative 0.06 volts. Okay, now what I need to do is look at basically the two different parts of this problem. So the first thing that I'm going to tackle is this right here. I've got my units, or I've got my numbers all squared away. So my equation, delta G equals RT, well, I have an R value. My R value is going to be 0.008315 kilojoules per mole times Kelvin times, well, this does tell me, actually, sorry, my question is, what is the change in free energy associated with transporting sodium plus into the cell at body temperature? So this is just asking me about the free energy. So this is asking me about the free energy, but I need to tackle the first part, the chemical potential, and then go on to talk about the electrical potential so that I can solve for the overall electrochemical potential. So this is my R, T, ln, and then I've got my concentration in my destination divided by concentration of my source equals negative 6.42 kilojoules per mole. Okay, I'm going to erase my doodling so that it's not distracting or anything. So I've got approximately 6 times the log of basically 15 over 150, or 10 to the negative first, which is just a rough estimate. It would show you negative 6. In the event that you didn't have your calculator or anything, you could kind of square things up like this. Okay, next up is my electrical potential. Well, Z sub A is my charge of my ion. I'm talking about a positively charged sodium ion, 96.485 kilojoules per volt mole times negative 0.06 volts equals negative 5.79 kilojoules per mole. Okay, so that also is going to be negative 6. So effectively what I'm doing is I'm looking at delta G equals negative 6.42 kilojoules per mole plus negative 5.79 kilojoules per mole equals negative 12.21 kilojoules per mole, which is effectively the same thing as negative 6 plus negative 6 equals negative 12. So ultimately what I'm looking at with this problem, so what we're looking at here is we could kind of break these out as two different things, the chemical potential and the electrical potential. Well, the chemical potential alone, based on the concentrations, is favorable, because a negative delta G, a delta G of negative 6. The electrical potential, well, that's also negative 6. So from an electrical standpoint, it's a favorable move. And so what we're looking at here is something that is, well, because of, you could kind of think about it as the chemical potential makes it favorable, but then the electrical potential makes the overall movement even more favorable. So if we did something like we switched this from a sodium ion to a chloride ion, well then you're probably looking at something a little bit different there, because Now you're not talking about the movement of a positively charged ion, so you'd have to change that Z sub A value right here. This is all my hypothetical using Cl minus. Well, then this value is going to change, in which case this becomes a positive 6, in which case whenever you add them up, the electrical potential difference basically negates the chemical potential difference. Alright, so now let's think about the same sort of question, or the same question that we just did, but rather than it going into the cell, we're talking about moving it out of the cell. Okay, so we've got the exact same setup. Now what we have is our cytosolic and our extracellular space. Well, these concentrations are going to flip-flop. So now we've got 0.008315 kilojoules per mole Kelvin times 310, same. But now our destination, our source has switched. So now we got 145 divided by 12. So this is a reaction which is overall negative, or sorry, a positive delta G, which is unfavorable move. Okay, so there's my quick summary. Now we've got the exact same thing. We've got a positive 1. Faraday's constant doesn't change. My delta G, however, it was negative, but now it's a positive move because we're talking about it going out of the cell. Okay, and so ultimately this move of a positively charged sodium cation going out of the cell is an unfavorable move because our delta G is going to be positive 12.21. So a last sort of explanation, or a last sort of inspection of this, now let's go ahead and just say we're not only moving our sodium ions out of the cell, but we're transporting 2 of them. What's that going to do? Well, if it took a delta G of positive 12.21 to push those sodium ions out of the cell, how about if we have 2 of them? Excuse me, I'm sorry. Well, our delta G for one molecule was 12.21. For 2 of them, it's going to be 24.42. So it doesn't change it a whole lot. In fact, it's really just, well, multiply by 2. Alright, well, I hope this is helpful, and I will see y'all in the next video.